So braking systems essentially convert energy in multiple ways. First, the kinetic energy from the vehicle is being converted into thermal energy when you apply the brakes. So when you step on the brakes, you're commanding a stopping force that sums to thousands of newtons of force. The basic hydraulic braking system, there's a really simple diagram on the right-hand side there that kind of outlines some of the main components. So the brake pedal, the master cylinder, the reservoirs, brake lines, calipers, and the rotor. So um, yeah, as displayed in the picture, when the driver pushes the brake pedal, force will be transmitted the pistons in the master cylinders. The pistons will apply the pressure to the fluid in the cylinder, and the brake lines transfer the pressure to the caliper. The pistons in the caliper move and apply the brake pad to the rotor, giving you that friction and that braking force. So yeah, the friction between the pad and rotor is going to generate heat. That's where the, uh, the thermal energy conversion comes in, and yeah, and I guess the second part there is mechanical to hydraulic energy. So that was covered a bit in the um, explanation of the picture, but the driver foot pressure on the brake pedal is being transferred. The mechanical energy is being transferred through the pedal into the balance bar, and that mechanical energy is being converted into uh, fluid pressure. Yeah, so the next slide here is comparing various types of performance brake rotors. So vented, drilled, and slotted. So starting off with vented rotors, commonly used on the front two brakes, and the most prominent advantage is improved heat rejection due to a greater increased total surface area of the rotor. Um, vented rotors will either have like linear or like angled slots, and like the benefit of angled slots is that it's I guess acts a bit like a pump, and there's more a dynamic, more of a dynamic advantage in terms of circulating the most amount of air through the rotor. Um, moving into drilled rotors, so uh, the individually drilled holes can become a little bit problematic because during ranges of intense braking, you're going to generate a lot of heat and the cooling as well. So this can lead to susceptibility of part failure and cracking. So for these reasons, it's not really ideal for racing. Drilled rotors are aesthetically pleasing though, and they can be built strong enough to last, hence why they are present on many high-end street cars. Um, okay, yeah, sorry. The third item here, slotted rotors. So this is the type of rotor we use on our cars, and the slots on the face of the rotor keep the brake pad clean and free to be, so that free of so that's a pro. Um, and as the pad moves over the slots, this can result in the brakes having a little bit more bite, which is also an advantage as well, with the trade-off that the brake pads will wear down a little bit faster. And yeah, on the right there, you can see a current image of the right or of the rear rotor design. Um, and it's important to note that it's the rear design because the rear and front designs differ. Specifically, the front ones are approximately 20% heavier. Okay, so the fifth slide here, hard versus soft brake lines. So steel brake lines have the benefit of being a little bit more durable due to just being made of a stronger material. However, for our application, it's not really a super important characteristic. Um, drawback that comes back with durability is and being made of steel is they're a little heavier and a little more expensive. So for our applications, they're not really ideal. A firmer brake pedal feel can also be attributed to steel brake lines, and this is due to another important factor that can be referred to as swelling in the brake line. So steel brake lines can withstand the pressure associated in the brake system a little bit better than rubber, and therefore they don't swell. Um, Going back to rubber, though, it's still possible to achieve a firm pedal feel, and they're much more commonly used, just being cheap and effective. And specifically for our needs, rubber is just clearly a better choice, just because you can see in the image on the right there, it's a really exaggerated illustration of what swelling is, but it's really, I mean, only going to happen once um, you've used a car for an extended period of time. So we build a new car every year, so that's not a concern at all. But um, yeah, rubber is clearly the better choice for us. Okay, so next moving into brake pads. So the first type is non-metallic, which is the softest type of brake pad, which essentially means you're going to have the accelerated wear, large amounts of brake dust, and it's going to be probably have the least wear on the rotor. So the non-metallic pads are made up of a combination of like glasses, rubbers, and metal fibers. It's relatively old technology and not uh, practical for many applications because there are a lot better options on the market, as we will see here. So moving into semi-metallic, and this is the type of pad we use for our car. So it's the most popular type of brake pad, constructed with a combination of both synthetics and metals to form a predominantly metallic hybrid compound. And finally, ceramic. So this is the most expensive type of pad, and it has the best thermal properties for high heat. This means that they can continually recover from whatever demands are placed in them, in events such as endurance racing. This feature, however, makes ceramics difficult to warm up to operating temperature, which can um, prove a hindrance for daily driving. So um, on the right-hand side here too, I included two images I just pulled. It's from the same website here, so they, I guess, do a good job of just comparing head to head. You can kind of see how the two top types of pads, so semi-metallic and ceramic, compare against each other. So yeah, the next important topic, brake fade. So brake fade is the reduction in stopping power that can occur after repeated or sustained application of the brakes, especially in high load or high speed conditions, such as endurance racing for our purposes. So um, yeah, I included two charts at the bottom here that kind of um, gives you a visual of what, where different types of brake pads have um, their optimal coefficient of friction. And so you can kind of see that, um, depending on what type of compound you're using, there is really a wide range that um, you can cover. So I guess it is really important to be strategic with um, the type of compound and the type of pad that you're going with. Okay, so the next and final important concept is uh, brake bias. So this is important for competition purposes because one of the requirements is that we're able to lock all four wheels at the same time for the braking test. And in order to achieve this requirement, you have to have the appropriate brake bias. Um, and just as I guess a quick summary, so brake bias is essentially what percentage of the braking force is going to the front versus rear wheel. So I believe for our car it's pretty close to 60-40, and I think that's pretty standard for most cars. So Moving into the next part here, how do we change and modify the bias? Um, so as previously explained, the mechanical energy from the brake pedal is transferred through the balance bar and converted into hydraulic pressure through the master cylinders. There are two master cylinders, one that is for the front two brakes and one that's for the rear two brakes. So the two different master cylinders have different bore sizes, and this corresponds to more or less hydraulic force. So the larger bore size will result in more pressure. So that's the master cylinder that corresponds to the front two calipers. Um, Additionally, a brake balance bar is used for fine tuning of the bias. A brake balance bar works by connecting the brake pedal to the two master cylinder push rods by a bar that pivots in the middle. Moving the pivot point closer to one side will increase the pressure on that master cylinder, moving the bias towards that end of the car. And yeah, the next one I want to talk about is just braking force. So um, braking force is really important um, aspect of understanding what your car is doing. So using MATLAB, it is possible to determine the respective output braking forces from pedal force input based on the sizing of the individual braking components. So um, yeah, like I didn't want to go too high level into specifically what that MATLAB was, but essentially it's really, you can easily isolate inputs and the correlation to the outputs, and using this code and that information, um, you're able to determine ideal sizing components for your calipers, master cylinders, mechanical advantage for the pedal, and the rotor radius. And then underneath there as well, I also just included some braking formulas that um, can be useful as well. I think one thing to note too is with the third point there, um, talking about the importance of downforce and the friction coefficient of the tires, and how um, both of those tools can be utilized to help us maximize our braking and get the most performance out of our car. Okay, so I just wanted to finish talking about drum brakes, just because they are pretty popular, and obviously we don't use them on our car, but um, they are out there. So yeah, just to finish up here, I think um, yeah, so in modern vehicles, drum brakes are mostly installed on the rear wheels, with the disc brakes being installed on the front wheels. Similar to disc brakes, as the brake pedal is pressed, it compresses the fluid in the master cylinder and allows the piston of the wheel cylinder to expand outward. The outward motion of the piston of the wheel cylinder forces the brake shoe outward against the brake drum, causing friction, and this is going to generate your braking force. So modern lightweight cars have rear brake drums mostly, um, just because the majority of the stopping is done by the front brakes, so it's not as important to have those more expensive caliper and rotor style on the rear wheels for those lightweight everyday drivers. Um, yeah, and I guess just to finish with those 2 points on the left or on the right there. So why do we still see them? Because they're less expensive and they're sufficient for most daily drivers. Why do they have less performance? Because they're less effective at dissipating heat, so you're more susceptible to brake fade, and they're less effective in wet conditions because water can pool inside the drum. So yeah, so that's everything I had. I hope you guys were able to take something from that. And I guess at this point, if there's any questions or comments, I can do my best to uh, try and answer any there. But yeah, thanks.